Think about translating a sentence. The input might be 5 words in English, and the output could be 8 words in French. The lengths don't match, the word order shifts, and yet somehow the meaning has to carry across. For a long time, neural networks had no clean way to handle that. Then in 2014, a paper from Google introduced Sequence2Sequence, and it gave us a template we still use today. Let's break down how it works and why it mattered so much. At its heart, Seq2Seq is 2 networks working as a relay team. Follow a sentence as it moves through the framework. First comes the encoder, originally in LSTM. It reads the input sequence 1 token at a time, updating its internal state as it goes. By the end, it has walked through the entire sentence and folded everything it saw into its final hidden state. Think of it as reading a sentence and building up an understanding word by word. That final state becomes the context vector, a single fixed-length summary of the whole input. This is the handoff point. Everything the encoder understood about the sentence gets compressed into this one bundle of numbers, and that bundle is all the decoder will get to work with. Now the decoder takes over. Starting from the context vector, it generates the output sequence 1 token at a time. It produces a word, and then it does something clever. It feeds that word back into itself as the input for the next step, which is what we call autoregressive generation. That feedback loop keeps rolling until the decoder emits a special end token. Because the output is built step by step rather than all at once, the input and the output can be completely different lengths. 5 words in, 8 words out, no problem at all. Now, to appreciate what this unlocked, compare it to what came before. Earlier neural setups mostly assumed a fixed shape, a certain number of inputs mapped to a certain number of outputs, which is fine for classifying an image, but hopeless for language. Sentences vary wildly in length, and you can't reword a whole model every time a phrase gets longer or shorter. Variable length mapping was simply out of reach. Seq2Seq solved that with the encoder-decoder split. One network absorbs an input of any length, the other emits an output of any length, joined by that context vector in the middle. Suddenly, translation, summarization, and dialogue all fit the same mold, and that clean framing became the foundation for modern generation. Let's lock into 3 ideas that define Seq2Seq. The encoder compresses the whole input into a context vector. Reading token by token, it distills a variable length sentence down to one fixed summary that stands in for everything the input meant. That compression is the core move of the whole framework. The decoder generates the output autoregressively. It produces 1 token, feeds it back in, and predicts the next, building the sequence left to right. This same generate and feedback pattern is exactly how today's language models write text 1 token at a time. And here's the catch that shaped everything after. Squeezing a long sentence into one fixed vector loses information, a real bottleneck. That very limitation is what attention was invented to fix, and following that thread leads straight to the transformer. All right, 4 takeaways to hold on to. Seq2Seq, from Seq2Seq and colleagues at Google in 2014, reframed translation as mapping one variable length sequence to another. It uses 2 recurrent networks. The encoder compresses the input into a context vector, and the decoder generates the output token by token from it. Because it generates autoregressively, input and output can be different lengths, which set the template for summarization, dialogue, and code. Its famous weakness, cramming a long sentence into one fixed vector, is precisely what attention was built to solve, and that line led to transformers. If you enjoy watching one idea flow into the next like this, Standarity.com is full of these explainers. See you in the next one.